Alrighty guys, let's go ahead and get started with some of these example problems. So the first one says, with the aid of a string, a gyroscope is accelerated from rest to 50 radians per second in 0.5 seconds. So first thing that we want to do is list all of our variables below. So I'll go ahead and start by writing theta initial, theta final, omega initial, omega final, alpha, and t. And then I'm going to look at my problem and I'm going to start writing what these variable values are down below. So theta initial is almost always just going to be 0 because we're starting at 0 degrees. Theta final is unknown. We don't know what that is. It says the gyroscope is accelerated from rest, meaning that our initial omega is just 0 radians per second. Well, it tells us that the final omega is 50 radians per second right here. And then the time is 0.5 seconds. We don't know what the alpha is, so that also is a question mark. So let's start by figuring out what the angular acceleration is. We have both omegas, time. We need to solve for angular acceleration, so we're going to go ahead and use little pup. We know that omega final is equal to omega initial plus alpha, it's a weird looking alpha, times t. Go ahead and plug my numbers in. I get 50 is equal to 0 plus alpha, which is unknown, times 0.5 as my t. Divide by 0.5, and I find out that alpha should be equal to 100 radians per second squared. Now that I have alpha, I can go ahead and figure out what the angular displacement is. So the angular displacement is going to be my theta final. I'm going to use my big dog equation up here to do that. So I have theta final is equal to theta initial, which is 0, plus omega initial, which is also 0, plus 1/2. The alpha, which we just got, is 100, times time, which is 0.5 squared. After you plug this in your calculator, you get theta final is equal to 12.5 radians. Now that we know what theta final is, our last part asks us to solve for how many revolutions it's going. Well, we know that 1 revolution or 1 rotation is going to be equal to 2 pi. And 2 pi is measured in radians. Therefore, I'm going to take my final theta here and divide it by 2 pi to figure out how many revolutions or rotations my object makes. When you're dividing it, make sure to put this in parentheses. Your calculators are really smart and they're going to do exactly what you tell you to do. And if you don't put it in parentheses, you're going to end up with the wrong answer. So after we solve for that, we get 1.99 rotations. Let's go ahead and solve for our second problem here. It says, suppose a fly lands on a vinyl record 0.05 meters from its center. The record is currently being played at 33 rotations per minute. What is the angular velocity? Well, we know angular velocity is measured in radians per second, so we're going to need to convert rotations per minute into radians per second. So I have 33 rotations per minute. First thing I want to do is convert minutes into seconds. 1 minute is equivalent to 60 seconds. So now my minutes cancel out. I have seconds on the bottom. And then next, I need to get rid of rotations. And I know that 1 rotation is equivalent to 2 pi radians. My rotations cancel out, and I'm just left with radians over seconds. Multiply everything through, and you get 3.45, 3.46, whichever you want to go with. I guess I'll go with 6 here. Radians per second as my angular velocity. Now that we have that angular velocity, we can go ahead and figure out the angular displacement. It says that the song is 7 minutes long. That's a really long song. And if we notice, it gives it to us in minutes. We know though that we want seconds. So 7 minutes is actually going to equal 420 seconds because I'm going to take 7 and multiply it by 60 because there's 60 seconds in a minute. So let's start out with theta initial, which is just 0, theta final, which is unknown, omega initial, which is 3.46, omega final, which is also 3.46. Because it's a record player, it's moving at a constant velocity there, so that's not going to change. Since my velocity isn't changing, that means that my acceleration is 0 in this case, and the time, which we just converted, is 420 seconds. Now that we have all this information, we can go ahead and solve for theta final. I can take my big dog equation, plug all my variables in above. I get 0 plus omega initial, which is 3.46, times my time, which is 420, plus 1/2 AT squared, where A in this case is alpha, and alpha is 0, so this is all just 0, doesn't matter. Go ahead and simplify. I get 3.46 times 420. That gives me a theta final of 1453.2 radians. Alright, now that I've figured out my angular displacement, I want to figure out what my linear velocity is. So in order to figure out linear velocity, I need to recall that velocity is actually going to be equal to the angular velocity times the radius. Well, I know what the angular velocity is because I solved for that earlier. That's just 3.46, and the radius in this case, it tells me up above, is 0.05 meters because the radius is how far I am from that center. So 0.05. All I have to do is multiply these two together, and I end up with a linear velocity of 0.173 meters per second. Last part it wants me to figure out is how far linearly does the fly travel. Well, I'm going to use a very similar equation I did to the velocity over here, where distance is going to be equal to theta times r. And the theta that I had was 1453.2, and r is the same r that I just used over here, which is 0.05. Multiply those two together, and you end up with a distance of 72.66 meters. Alright, so for this problem we have a string that is wrapped around a yo-yo whose center shaft has a radius of 0.25 centimeters while performing a trick. The string is pulled with a linear acceleration, just meaning a, of 2.6 meters per second squared. What is the angular acceleration? Well, we know that angular acceleration is equal to our linear acceleration divided by the radius. The linear acceleration is 2.6 meters per second squared, and the radius is 0.25 centimeters. So we need to convert that into meters because we know that acceleration is in meters per second squared, so we need to be in meters in order for this to work. So now all we do is take these two numbers, plug it into our equation, 2.6 divided by 0.0025, and we find out that our angular acceleration should be 1040 radians per second squared. Alright, now that we have our angular acceleration, it wants us to figure out our angular velocity after 0.8 seconds, assuming it starts from rest. Starting from rest means that our initial angular velocity is just 0. So if we list our variables really quickly, we know what alpha is. We know time is 0.8 seconds. We know that the initial angular velocity is 0, and we're solving for that final angular velocity. So we have time, initial velocity, acceleration, and we're solving for final velocity. That means that we're going to use little pup over here. So we get omega final is equal to 0 plus 1040 times 0.8. Multiply these two together, and we find out that our final angular acceleration should be equal to 832 radians per second. Now that we know our final angular acceleration, it asks us to solve for the linear acceleration of the yo-yo at the edge. We know the outer radius of the yo-yo is 3.4 centimeters. So to do that, it's very similar to what we did in problem number 1, where we had angular acceleration is equal to linear acceleration divided by radius. This time we know the angular acceleration, it's 1040, and we do not know what the regular acceleration is. We know that the radius at the point at which we're at this time is 3.4 centimeters, also known as 0.034 meters. In order to solve for acceleration, we're going to multiply this guy over here, and we find out that the linear acceleration should be equal to 35.36 meters per second squared. So let's take a look at this next problem. We have a round object with a radius of 0.45 meters rolling down an inclined plane that is 6 meters long. The object is released from rest, and it takes about 3 seconds to reach the bottom of the ramp. We want to figure out what is the rotational acceleration of this object. So first thing I recommend we do is list our variables. We know that the radius is 0.45 meters, so I'm going to list that down below. Next, I'm going to start listing my linear variables, and I'm going to start with my initial distance, which is just 0 meters. Then my final distance would be the final length of the ramp, which is 6 meters long. From there, I'm going to list my initial velocity. It tells me that it's rolling down and that it's starting from rest. That would be 0 meters per second. My final velocity is unknown. I don't know the final speed. My acceleration is also going to be unknown. And then the time it takes to reach the bottom is 3 seconds. Now we're going to go ahead and list our variables in the rotational plane. We have theta initial, which is just 0, theta final, which is unknown at this moment. We have omega initial, which is also going to be 0 because initially it's not rotating. And we have omega final, which is also unknown. We have alpha, or the angular acceleration, which is also unknown. And then we have time, which is still just 3 seconds. If we look at all of our variables, we can see that we're actually going to have to start with linear kinematics in order to solve for stuff, and then convert it over to rotational. So let's go ahead and start using our linear variables, and we're going to solve for acceleration first. So the equation we're going to use is big dog, where we have df equals do plus vot plus 1/2 at squared. Our df is 6, do is 0, vo is 0, and then 1/2. A is unknown, and t is just 3. Can't forget to square it though. Now we're going to simplify our equation where we get 6 is equal to 4.5 times a. Go ahead and solve for a. We find out that a should be equal to 1.33 meters per second squared. Now that we have a, we can go ahead and convert that to alpha. We know that alpha is equal to a divided by r. A is 1.33, r is 0.45. So go ahead and solve for this really quickly, and we find out that alpha, or the angular acceleration, should be 2.96 radians per second squared. Now that we have the angular acceleration, let's go ahead and solve for the final angular velocity, or omega final. We're going to use little pup to do this, where omega final is equal to omega initial, which is 0, plus alpha times t. Alpha is 2.96 and t is 3. Multiply the two together, and we find out that omega final should be equal to 8.88 radians per second. Last variable we want to try to solve for now is our final theta, and we're going to go ahead and use big dog for that, where theta final is going to be equal to theta initial, which is 0, plus omega initial, which is also 0, times time plus 1/2 alpha times t squared. Alpha was 2.96 and t was 3. Once we simplify all this, we find out that theta final should be equal to 13.32 radians. Now that we know the final theta, We can go ahead and use that to figure out the amount of rotations or revolutions this ball is going to make as it rolls down the hill. We're going to take our 13.32 radians and divide it by 2 pi, and that's going to tell us that our ball is going to rotate 2.12 times. Another way we could have figured this out is by taking the radius, which is 0.45 meters, and the total linear distance that it covers, which is 6 meters, and finding a relationship between that. Well, we know that one revolution would be one circumference, so the circumference of the ball is 2 pi r, and the distance is 6 meters. So if I take my distance of 6 meters and divide it by the circumference, I can find out how many total rotations my ball makes. By doing so, I end up with the exact same answer, which is 2.12 rotations. Lastly, we want to find out the linear final velocity of that ball at the bottom of the ramp. And to do that, we're just going to take our angular velocity and multiply it by the radius to find that. So we get 13.32 times 0.45, and that's going to give us a final velocity of 5.99 meters per second.